Okay, quiz 15.2 is how to work with Q and K, a little bit mathematically. And so here we have a reaction H gas plus Br gas in equilibrium to form HBr gas. And these are individual atoms. They aren't elemental hydrogen and bromine, they are individual atoms. And I'm going to go ahead and call this reaction star. That's the one that we're interested in. And question 1 says, can we calculate the value K, equilibrium constant, from all of these other reactions? So I will call them reaction A, which is H2 in equilibrium with 2H. And everything's a gas, so I'll leave that off, just because I'm lazy. And B is Br2 in equilibrium with 2Br. And C is going to be Br2 plus H2 in equilibrium with 2HBr. And our task is, can we come up with some formula to recreate our equation of interest out of these? And it's pretty straightforward because each of our components of the reaction of interest appear in only one way here among these. So I need a hydrogen on the reactant side. The only hydrogen I see right here is in reaction A, and it's in the product side. So I'll say negative 1/2 A. The negative will reverse it, and the 1/2 will change that from a 2 to a 1. We can kind of keep track of everything down here. Once I've taken 1/2 A, I will have hydrogen on this side and 1/2 H2 on that side. Well, the same thing for the bromine. It only appears in B, so I'll do the same sort of trick, negative 1/2 B, and that will give me a bromine on this side, and give me a 1/2 of a Br2 on that side. I reverse it and cut it in half. And then I need an HBr on the product side. C provides 2 HBrs on the product side, so I will add 1/2 of C, and that gives me the HBr over here that I need, and it's going to give me 1/2 of hydrogen and 1/2 of bromine over there. Now let's cancel some things out. 1/2 H2 cancels, 1/2 Br2 cancels, and I'm left with what I wanted. So this is a valid formula. Now how do we use this formula here to get the equilibrium constant? Well, K star is going to equal, we'll take the inverse of A and square root it. So we'll have square root of Ka. We'll invert it because of the negative, square root it because of the 1/2. Then we'll take the inverse of B and square root it as well, times the square root of Kb. And then we're adding C, so we'll just multiply by Kc, but we'll square root it there. So times the square root of Kc. So this formula here for recreating the chemical equation is going to lead to this formula here for calculating its equilibrium constant. And so this is going to equal the square root of 2.78 times 10 to the third over the square root of 11.8 times the square root of 1.15 times 10 to the negative 5th. Put all that into your calculator and you get 4,500 30. So question 2 says if the system has reached equilibrium and you measure the HBr concentration and the hydrogen concentration, can you find the bromine concentration? Well, we know that the equilibrium constant 4,530, that is going to equal the concentration of HBr over the concentration of H and the concentration of Br. So 4,530 is going to equal 0.025 divided by 0.0015. Those are the concentration of HBr and the concentration of H times the concentration of Br. Now we just solve for that Br concentration. Just multiply it over here, then divide the 4,530 on this side, and you end up with 0.0037 molar. That is the concentration of Br. Can we find the reaction quotient Q under this particular set of conditions and determine which way the reaction might shift? So Q will have this same form. The concentration of HBr that we're given is 0.0035 molar, divided by the concentration of hydrogen, 0.020 molar, times the concentration of bromine given, 0.0025 molar. And I could have left off those units because for Q and K, the units just disappear. But anyway, put those numbers in your calculator and you end up with a Q equal to 70. Now, if K is 4,500 and Q is only 70, that means that Q is less than K under these current conditions. And that means that the reaction will shift to the right toward products. Okay, so we have the reaction of H2 plus I2 going to HI, and the equilibrium expression for that would be HI squared over, where are we, H2 times I2. Right? And we can tell that based on the balanced chemical equation given there. We have the products raised to the power of their stoichiometric coefficients over the reactants raised to their stoichiometric coefficients. And so we can just plug in these values. That would be 0.90 squared divided by 0.05 times 0.05, and that's going to give us a K equal to 324. Now, this bonus question here says to compare the K values for the production of HBr and HI from their elemental constituents. So question 4 was the formation of HBr from its elemental constituents. If we come up here, it's actually the third equation here, the one that I called circle C, that forms HBr from its elemental constituents and is the proper one to compare. Our reaction of interest up here was formed from atoms which are not the elemental forms of hydrogen and bromine. So we want to look at this. 2,780 is the equilibrium constant for the formation of HBr. And then in question 4 we solved 324 is the equilibrium constant for the formation of HI. That means that the formation of HBr has an equilibrium constant that is larger, it is more heavily product favored, and that means that HBr is more stable than HI. HI is less stable than HBr. Okay, just by comparing, the 324 is less than the 2,780. And this is interesting because it is a way to explain why, although HBr and HI are both strong acids, HI is a slightly stronger acid than HBr. The HI molecule is a little bit less stable. It's a little bit more ready to give up its hydrogen than HBr is. And it's a bit of a weak argument, but we're at least getting at trying to explain structurally why acids have different strengths. And we're doing it in this admittedly a little bit simplistic way by looking at the equilibrium constants for their formation reactions.